Integration by parts, part 1, an introduction. Integration by parts is an advanced technique that I often call IBP and that I like to think of as an anti-product rule, sort of. I'll explain what I mean by this a little bit later. But it is an advanced integration technique, and anytime we're doing an advanced technique, we want to know, when should I use this? That is, what is the rule that says when this happens, I should do integration by parts? Unfortunately, there's not a hard and fast rule, but there are some indicators, at least ones that I look for. And the indicators that I look for is that if I see that the integrand is a combination or a product of the following functions, then I know it's probably going to be an integration by parts. So the functions that I look for are x to the n, where n is an integer greater than or equal to 0, or cosine of x, or sine of x, or e to the x, or natural log of x, arctan of x, arcsine of x, etc. But these are the main functions. So if I see an integrand that is a product of one or more of these, I'll show what I mean by one or more, then I think it's integration by parts. So let's look at some examples without actually doing any of the work. So if I see x squared times sine of x, I know that's integration by parts. If I see e to the x times cosine of x, integration by parts. If I see natural log of x on its own, it's a little bit more of a disguised one, but this is integration by parts. So I could think of natural log of x as x to the 0 times natural log of x. That's what I mean by a product of one or more of these up here. But let's see where this rule comes from. So to start, let's define a couple functions. Let u be a function of x, and v be a function of x as well. So later on when we write u and v, we know it's really u of x and v of x. And let's take the derivative of u times v. Well, that's the product rule, which says let's take the derivative of the first piece, leaving the second function alone, plus leave the first part alone, times the derivative of the second function. And we end up with this, the end result of a product rule. Now, we can multiply everything by dx, which will leave us with d of uv equals, I'll rewrite this so it's a little prettier, v times du plus u times dv. Now, what if we were to integrate both sides? It seems kind of weird to do, but because we just took the derivative, but let's do it anyways. So if I integrate both sides, and I can integrate each piece separately, I would end up with uv, because the integral of d of something is that something, equals the integral of v du plus the integral of u dv. We're going to rearrange this, and I'm going to put this piece here on the left. So if I have the integral of u dv equals uv minus the integral of v du. Now you might think, that doesn't really help. It looks more complicated That is, we would start with something like this, and to solve it, I would need to do all this. That looks more complicated, but if we choose wisely, we'll actually get something on the right side of the equation that's easier to solve or even solvable, whereas the integral on the left side may not be. Let's do a quick, very simple example. Let's do the integral of x times sine of x. Now, I recognize this as integration by parts. I don't know how to do it, or I don't know the answer. Use substitution. Integration by substitution doesn't work. So at this point, I don't have any other techniques, so it must be integration by parts. But I also have this indicator up here that is a product of x to the n times sine of x. So I know that the integral of u dv is uv minus the integral of v du, where we're given u dv. More specifically, we can choose u, and then whatever's left over will be dv. Now, what should I let u equal? Well, I could either let u equal x, which makes dv equal to sine x dx, or I could let u equal sine x, and then dv will be x dx. So let's look at these two side by side. Notice I'm starting with u and dv. I need to find v on the right side, and I also need to find du on the right side as well. So looking at my choice on the left, if u is x, then du must be 1 or 1 dx. And if dv is sine x, then v is negative cosine of x. We don't need the plus c. We'll put that at the very end. If I plug in, I get the integral of x times sine x. That is, the integral of u dv is u times v, negative x cosine x, minus the integral of v du. Equals negative x cosine of x plus the integral of cosine of x. Notice how this integral is way simpler than the original. In fact, we can continue on and solve this one. I get negative x cosine x plus the antiderivative positive cosine is positive sine. And now, at this part, I put plus c. But what if I had chosen a different u? What if I let u equal sine x, which would give me du as cosine x dx? And if dv was x, then v would be x squared over 2. Plus c we'll use later on. If I were to rewrite my integral of u dv, I would get uv x squared over 2 times sine of x minus the integral of v du. But notice that this new integral is arguably more complicated than the original. So it looks like my first choice was the best choice. Experience will tell you what to do, what to choose for u, what to choose for dv. And I recommend messing up, because if you mess up a time or two like I did over here, you start to see what you should have done a lot better.